Here is a number that has been inside a doctor's office, an insurance form, and probably your own medical record, your BMI, body mass index. A single number that tells you whether you are underweight, healthy, overweight, or obese. But here is what almost nobody knows. The number was not invented by a doctor. It was not invented by a nutritionist or a public health researcher. It was invented by a Belgian astronomer in 1832, a man who was trying to describe the perfect human being using the same math he used to track stars. And the deeper you look at that story, the more you realize it raises a question that sits at the heart of modern science. When we assume that data follows a bell curve, that human bodies, natural phenomena, social behaviors all cluster around the neat, predictable average. Are we discovering a truth about the world, or are we projecting one onto it? That question is almost 200 years old, and we are still answering it. Adolphe Quetelet was born in Ghent in 1796, and his life began with loss. His father died when Adolphe was 7 years old, leaving the family in financial precarity. There was no obvious path forward for a fatherless boy in early 19th century Belgium. But Quetelet had something unusual, a mind that would not stay still. By 19, he was teaching mathematics. By 23, he had earned the first doctorate in mathematics ever awarded by the newly established University of Ghent. His dissertation was on the geometry properties of conic sections, elegant, abstract, precise. He could have stayed there in the clean world of pure mathematics. Instead, he went to Paris. In Paris, Quetelet studied probability under Laplace and Fourier and moved in the circle that included Poisson, the architect of a new science of reasoning under uncertainty. They had built the mathematical tools for extracting signal from noise, for understanding not just what happened, but what was likely to happen. Quetelet absorbed all of it, and then he came home with the question that no one else was asking. He had been appointed to build and direct the Brussels Observatory, a place designed to measure the heavens. And as he set up his instruments and began training his astronomers, he noticed something that would change his life's direction entirely. When multiple astronomers measured the same star, they never got exactly the same number. Each observation was slightly different. And yet, when you plotted all those measurements together, they formed a shape, a symmetric, bell shaped curve. The true position of the star sat at the center. The errors clustered around it, falling away predictably in both directions. Astronomers had a name for it. They called it the error curve. Gauss had described it mathematically. It was a tool for correcting mistakes in celestial measurement. Quetelet looked at that curve and asked a question that was either brilliant or slightly mad, depending on your perspective. What if that curve wasn't just describing measurement errors? What if it was describing natural itself? To test his idea, Quetelet needed data, not stars, but people. He gathered high data from French military conscripts, thousands of young men measured and recorded for the purposes of military fitness. He plotted the data, and there it was, the bell curve. Human heights distributed symmetrically along a central value. falling away in both directions, just like astronomical errors around the true position. Later, he would publish chest measurements of 5,738 Scottish militiamen, and again the bell curve appeared, fitting the data with remarkable regularity. Quetelet drew a conclusion that would echo for 2 centuries. Human physical traits measured across a large population follows the normal distribution. The variation you see in any crowd, the tall and the short, the broad and the narrow, is not chaos, it is mathematical order. He called the center of that distribution Ilman Moyan, the average man. And here is where his thinking took a turn that feels strange to modern ears. He did not see the average as merely a midpoint. He saw it as an ideal, a standard of beauty, the perfect human form from which real individuals deviated like errors around a true value. The Elfman was not a real person. He was a mathematical abstraction. But Quetelet believed that by understanding him, you could understand the population, and by understanding the population, you could begin to govern it wisely. This was the birth of what he called social physics, the idea that human society, like the physical world, follows deep, stable mathematical laws. And if you collect enough data, the noise of individual behaviors average out, and something true and regular emerges underneath. And to make that idea concrete, he invented a tool in 1832, studying how human weight and height related to each other across the lifespan. He noticed a pattern. In adult life, weight does not scale linearly with height, it scales with the square of height. And he created a ratio, weight in kilograms divided by height in meters squared, a single number to describe where any individual stood relative to the average human form. He called it the Quetelet Index. 140 years later, a researcher named Ansel Keys renamed it the Body Mass Index. You know it as BMI. The reach of what Quetelet set in motion is almost impossible to overstate. He did not stop at physical measurements. He turned his methods on crime statistics, on suicide rates, on marriage and birth records, and found the same thing everywhere: regularity, patterns, bell curves emerging from what it looked like human chaos. He famously wrote that society pays a tax of crime with frightful regularity, that you could predict year after year how many murders, how many forgeries, how many violent acts would occur simply by understanding the social conditions that produce them. Crime, in his framework, was not just a moral failure of individuals, it was a measurable output of societal forces. This was a revolution. For the first time, government had a scientific argument for why social conditions, poverty, education, unemployment, were not just moral concerns, but statistical predictors. Policies could be evidence based, interventions could be targeted. In 1853, Quetelet organized the first International Statistical Congress in Brussels. Delegates from across the world came to agree on how nations should count their citizens, classify their death, record their lives. The work that began in that room is the direct ancestor of the International Classification of Diseases, the ICD, the system that every hospital in the world uses today to record why people die. Among those later drawn into his orbit was the young man who would become Prince Albert, husband of Queen Victoria, one of Quetelet's mathematics students in Brussels during the 1830s, who later helped connect him to the leading scientific minds of Britain. Florence Nightingale, who met Quetelet at the 1860 London Statistical Congress, shared his near religious conviction that data was a map of truth. That by reading it carefully enough, you could see what needed to change and change it. The normal distribution became the default assumption of modern science in medicine, in psychology, in economics, in engineering. If you were measuring something about the population, you assume it was normally distributed unless you had a strong reason to believe otherwise. That assumption made an enormous amount of mathematics tractable. It made statistical inference possible at scale. But Quetelet's legacy carries a shadow that cannot be ignored. His idealization of the average, his insistence that the mean was not just typical but perfect, that deviations were nature's errors, gave a later thinker named Francis Galton a framework he would take in a catastrophic direction. Galton took Quetelet's bell curve and asked, what if, instead of celebrating the average, we selected for the extremes? What if we could improve the human population by controlling who reproduced? That question became eugenics, one of the most destructive pseudoscientific movements in history, responsible for forced sterilizations, discriminatory immigration policies, and ideological scaffolding for atrocities. Quetelet did not intend this, but the intellectual path from his average man to Galton's eugenics is short and direct. And the normality assumption itself, the foundation of so many modern statistics, break down more often than textbooks suggest. BMI, Quetelet's most visible legacy, is now widely criticized. It was derived primarily from data on European men. It does not account for age, sex, muscle mass, bone density, or ethnic variation. It classifies Olympic athletes as overweight and misses metabolic disease in populations where risks appear at lower weights. The single number that was supposed to describe the average human form turns out to describe a very particular slice of humanity, and not always accurately even there. And the normal distribution, for all its power, is simply not universal. Here is one thing worth carrying out of this story. The normal distribution is a powerful assumption, but your data has to earn it. Quetelet was not wrong to look for mathematical order in human variation. He was right that it exists, that the large populations follow patterns, that those patterns can inform policy and science and medicine. But he made the assumption too quickly, apply it too broadly, and idealize it in ways that had consequences he could not foresee. In my own work with climate data, I run into this regularly. Wind speed is one of the most important variables in environmental monitoring, for wind energy modeling, for storm risk assessment, for climate projections. And wind speed does not follow a normal distribution. It often follows a Weibull distribution. A flexible, scaled curve that fits the reality that wind speed is always non negative and that calm and moderate speed are far more common than extreme ones. Even the Whipple distribution has its limits. In strong cyclone conditions, engineers turn to extreme value distributions to capture risks that standard models miss. So, if you assume normality and apply it to wind speed data, your model will underestimate extreme events. In climate science, that is not an abstract statistical error. It has consequences for infrastructure design, for energy policy, for how we prepare for the storm that are coming. Quetelet told us to look for the curve. The work he left us is learning to ask every time with every data set which curve it actually is.